Okay. Now, if we want to measure the rate of reaction, first thing we need to know what is the meaning of the rate of reaction. So as long as involve the word rate of reaction, in this case, always remember we are going to use the time. Means that we have to divide something over time. Then I will get the rate. Are you clear? So this something means something that we want to measure. Something that we can measure here. Okay, you don't tell me, oh, color change. Then you won't be able to give us a measurement. So it must be something that can be measured. Okay, so the reaction rates, rate of reactions in the enzymatic reaction is defined as very simple, how fast or slow a reaction take place. And we can measure it by determining the rate through the measurements of how fast we can form a product or how fast the substrate can disappear. Okay, so we talk about this, the formation of the products. So in terms of the example, rate of formation of the products, how fast a product can be formed, we must be something that we can measure. Always remember, we must use something that we can measure. Okay, so how we measure? We can measure, for example, in this experiment, we measure the, okay, we measure how fast the gas is collected. Okay, because in this experiment, catalyst is an enzyme that break down the hydrogen peroxide into the water and oxygen. So the reaction is equation is this. Okay, hydrogen peroxide H2O2. When you break it down, you get the H2O and O2. So you balance the equations. It should be 2 and 2 here. Okay, you balance the equation. And according to this is the liquid stage, H2O2, and H2O again liquid stage, and O2 is the gas. So we can collect the gas and make sure that, okay, to measure the volume of the gas that we collected. So the oxygen that is released can be collected at a fixed time interval, and we can measure them. So this method is called downward water displacement technique. So in this activity 4.5, you can see that in the diagram is a setup for catalyst hydrogen peroxide reactions. So I didn't label, so perhaps you can label here, guys. So in this case, this is the hydrogen peroxide. Okay, so we do have this, okay, catalyst. So because of reactions, then we have the O2. So O2 release. So O2 will be channeled into this inverted burette. So in this inverted burette, then we will be able to see, how much gas will be collected here. So if you plot a diagram, a graph, how you show your expected results here. Okay, so what you plot in this case? Okay, you sketch a graph. So this graph is termed as, okay, products, okay, or volume of O2 release. Correct. O2 and volume of O2 release in cm3. And then this one will be times, correct? Okay. So what you expect your graph will be? Because initial rate of reaction always higher, so you tend to get a curve. Okay, but we do know that a certain period of time as enzymatic reaction stop because no more substrate already. So therefore, at time 0 here, you can see that we don't have any products formed, and it continue to increase, and then it slow down, and then it gets a plateau. Okay, and this we call as a level off. Okay, so this is what you expect to see. Okay, if you measure how fast products can be formed. Okay, any questions so far, guys? Okay, so basically you can see that increase and then become plateau. Okay, so this plateau is due to what? This plateau because of the what we call this the substrates You finish already, right? You try to imagine. First, I collect, okay, 10. Okay, after 1 minute, let's say 10 ml. After second minute, continue, accumulate. After that, you see that, how come no increase already? Okay, cannot increase anymore, right? Because volume of O2 release remain constant now. Even though the time progress, time still continue, tick, 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 time still continue, but my product form is still remain the same. So when it remain the same, basically means that the reaction has stopped already. So stop due to what? Now, this one we need to know later, okay? We have a lot of the reason why the process stop, okay? So alternatively, we can actually measure the rate of disappearance of the substrate, okay? So in the amylase starch experiment, amylase break down the starch to the reducing sugar called maltose. So this is a hydrolysis process. So what we can do here is we can actually check on the starch using the starch test. Basically, the reagent is iodine solution, highlights iodine solutions, not iodine. Okay, so during the reactions, every time we can collect some sample, sampling out, and then we can actually test for the presence of the starch. Okay, so as the starch is converted into the maltose, so the concentration of the mixture decrease. So therefore, you can see that you will see the change from the blue-black to the brown or even the yellow-brown. Okay, so if you look at this process, guys, you can see that at first, okay, let's say, for example, 0 second, after that 10 second or 15 second, 30 second, 45 second, and continue. At the end, you can see that's now no more color change already. It's iodine color, for example. But the thing here is, if you want to measure the rates, I must have something that I can I can measure something. So I must have something that I can measure, must be measurable. But color, how we measure the color? I know that, oh, reaction stopped already. I know, but how you measure? Can you see that? So if I want to measure the color, then we can use a machines or instruments known as colorimeter. Okay, so the instruments here is known as colorimeter. Be careful when you write it, it's not CA, but CO, color. Okay, always remember color. And colorimeter, very, very important. Colorimeter won't tell us the color. Definitely, they won't tell us the color. What they do, a colorimeter actually measure or determine highlight color intensity. What they do, they actually measure the absorptions of different wavelength of light. Okay, they measure the absorption. Okay, so therefore, the color intensity here can act as a measure of the concentration of the starch that still remain. Okay, so how this instrument actually function? So colorimeter, one of the example of colorimeter is known as spectral photometer. So actually consists of two parts, this instrument. So one is called spectral meter, another one is called photometer. Okay, this instrument actually have two sides. One is the one, okay, this part, can you see that? This part is known as the spectrometer, okay, spectrometer. And this part is known as the photometer. Okay, clear? So we can place our sample in between of these two. We can place our sample here, can you see that? Between the spectrometer and photometer. So what is the function of spectrometer? Spectrometer, basically, we're going to have this colorimeter. Colorimeter basically is something like a lens to focus the light. We have any light source. We do know that lights consist of different wavelength, correct? So it doesn't matter. What we're going to do here is we're going to focus this light onto a prism. So this prism going to have these diffractions. So therefore, we get different wavelength. And then we can have the wavelength selector here to select a particular wavelength. Let's say, for example, I allowed the yellow lights to pass through. Okay, so when yellow light pass through, because of a sample, now you have to understand, not all. Let's say, for example, when you look at let's say, I look at this. Now, if something is red color, So what actually happened? Because our light consists of three basic color, correct or not? The light, the white light or visible light actually consists of three different color, a mixture of these three different color. First, we have red color, the R. Then we have the blue color, B, and green color, G. So when these three color, okay, with different light wavelength hits on my sample, what will happen here is they were going to absorb some of these lights, are you clear? And reflect a particular light. So that's why we look at it red color, because in this case, red color reflected. So when we see it here, that's why it appears as red color. How about the blue color and the green color? These two lights will be absorbed. Are you clear? Because these two lights will be absorbed, therefore what we see actually is red color. Clear or not? Okay. Now, what actually happened here is similar to our sample. Okay, so if I give them a particular wavelength, So look at this, I give them. So in this case, if I only give the red color, what will happen to my sample? If I give only red color, I will see as a red color. Correct? Because why? Red color going to be reflected. Okay, a solid object. But if I give them the blue color, what I can see? If I shine with blue color, because all blue color lights will be absorbed, so means that I will see as no light, no reflection. I will see as black color because no reflection of light. Okay, why? Because the blue lights will be absorbed. If I give them the green color lights, so green color lights will come, and then what will happen? Again, will be absorbed the green color lights, so therefore nothing we can see. Again, is the black color. So black color is not really, we see as a black color because no color or no light is reflected, so that's why it's black color. So what will happen here is if I choose one wavelength and allow the light to pass through a particular wavelength, okay, the light to pass through, what will happen here is some of this energy or light intensity will be absorbed and some of them will be allowed to be transmitted. So now we have this I intensity before entering into, can you see that? The I naught basically means that intensity of the light that enter into or pass before they pass through my sample. And I have this intensity of the transmittance. The IT stands for transmittance. So we can measure this transmittance. When I measure transmittance, then I will be able to calculate how much it absorbs. So the higher the absorption means that the higher the concentration, or highest this is what we call the intensity. Are you clear? So what we measure here is the absorbance. Do you get what I mean here, guys? Okay, so a spectral photometer make up of two, okay, instruments. Here we have a spectrometer and also the photometer. The spectral meter produces a desired range of wavelength of the lights. So we have the collimator here to transmit the lights, okay, and pass it through a particular prism here, so that we can actually later we have this selector to select a particular wavelength and allow these lights to pass through my solution. So we place our solution in a container. This container is known as cuvette. Cuvette is this container. Okay, so the photometer now detect the intensity of the photons. Photon means the light intensity that is absorbed, and then send a signal to the galvanometer or a digital display. Can you see that? So I detect how many, and then I convert. I will show you the absorbance. So this one is the absorbance data. Okay, the absorbance. Okay, sorry. Okay, the absorbance data we can see here. So if the absorbance is high, so it means that the concentrations of the particular thing is high. So what's the particular thing? So starch, no? the blue blacks, right? So blue black means they absorb a lot. The yellow means they absorb less. So therefore, you can see that we will be able, in this case, to identify how much starch can be formed. But we didn't measure starch directly. What we measure the iodine complex there. Okay, iodine starch complex. Okay, the form blue blacks. So the spectral photometer is designed in a way that the liquid sample is placed between the spectrometer and the photometer measure the intensity of the light that passes through the sample. We call it transmittance, and deliver a voltage signal to the display. If the absorbing light absorbance change, the voltage signal also will change. Okay, so if you go and read it up more, transmittance is calculated. Okay, transmittance T is calculated as I transmitted over the I naught. Okay, if you want to calculate, so you can calculate how much transmittance, okay, the intensity of the light that transmits across or through your sample divided by the light initially. So you get a percentage. Then you can convert it to the absorbance. So absorbance will equal to negative log IT over IO. Okay, so these are two formulas that you are not required to know, just for informations only. So what is meant by transmittance? Transmittance basically is the intensity of the light that pass through, a fraction of the light that pass through the sample. So what is absorbance? Absorbance basically is a negative log of the transmission. So it means that we will be able to calculate this absorbance. So the higher the absorbance means that the concentration is higher. So what we measure here in this case, we measure the starch. So now look at this. If I use it, okay, every sample I put in the cuvette and measure the color intensity. What we measure here, we call it a color intensity. So means that I will be able to plot the graph. Because color, I can't plot the graph. I cannot say, oh, blue, black, brown, dark brown, and then light brown or yellow brown. I can't plot the graph. So with the help of the colorimeter here, colorimeter can give us the reading of absorbance. So this absorbance also termed as the color intensity. Are you clear? The absorbance also known as color intensity. So again, guys, when you write down what is the function of colorimeter, this colorimeter, always remember, don't write, oh, determine the color, because colorimeter won't be able to determine the color. They will determine the absorbance or the color intensity for us. Okay, so how you plot the graph now? Okay, so for this, you plot the graph. Because it's disappearance, right? Okay, disappearance of the substrates. So this is T, the time. And then this one you can plot as an absorbance. Or you can plot it as color intensity. Either you write absorbance or you write it as color intensity. Okay, so color intensity actually don't have units. Okay, normally we just say as an arbitrary unit. Okay, so no, either it's no units or arbitrary units, or even sometimes we use percent. Okay, percentage of absorbance. So what do you expect to see the graph? Increase or decrease? The color intensity initially, if at 0, time t equal to 0, so blue black. So blue black basically they absorb a lot of light energy intensity, right? So therefore absorbance will be very high. They absorb a lot. Okay, so but at the end, let's say 10 t equal to 10. So now yellow brown. Here, yellow brown definitely transmit more light compared to the blue blacks. Okay, but it's still absorbed, right? It's still absorbed. Okay, some of the light. So therefore, you can see that the graph will show us the decrease and then plateau. Okay, so it won't go to 0. It won't go to 0. Okay, because if it go to 0 means that everything transmitted, no absorption at all, pure water. Even pure water, you also have some absorption. Are you clear? Okay, so this is how the graph look like. This is t equal to 0. Clear so far? Any question? Yes or no? So the next part of the topics here, we're going to look at the cause of a reaction. So basically, we are going to follow the cause of reactions. Okay, what actually happened in this case. Okay, so we use the catalyzed hydrogen peroxide reactions so that we actually measure the how fast products can be formed. Okay, so the rate of enzymatic reactions we can actually calculate by finding the gradients of the curve. So this is a little bit of confused because when it's a gradient of the curve, and you look at the curve, we have different regions of the curve, and different region of the curve actually will give us different what we call these values, right, of the gradient. So you have to understand the question, because if we want to find the rate of enzymatic reaction, then we need to know that we have three ways to measure, okay, or to determine the rate of reaction. We can measure the rate of reaction at the initial point. So we term it as the initial rate of reaction. So if you want to measure the initial rate of reaction, if the question said that, okay, measure what is the initial rate of reaction, so we always place our tangent. Can you see that? The tangents of the curve nearest to zero. Okay, you place the tangents to the nearest to the zero, and then we calculate the gradient. So this one is the d delta. Yeah, a bit mathematics now. So this one is dp. This one is dt. So the rates actually equal to the dp over dt. So P means product, concentration of the products. The change in the concentration of products divided the change of the times. So this is called the rate. D stands for the change, okay? The change. You learn about the differentiations, right? So this is something called dP over dt. Okay, dP dt in this case basically indicates the rate, how fast products can be formed here. So in this case, I get the time nearest to zero, okay? Therefore, I will get the initial rate of reaction. I also can measure the rate of reactions at particular time. Then in this kind of question will tell you what times. For example, I want to know the rate of reaction at this point of time. Then I place my tangents at this point, and then I measure the rate of reaction. So this is a particular point. Or I can measure, the overall rate of reaction. Overall rate basically means that I need to know when the reaction stops. So in this case, I can measure what? I can measure, okay, reaction actually stopped here. Can you see that? So then I get this is overall times, this is overall products. So I will get overall. So in this case, I will get my rates equal to the overall product, concentration of the product divided by overall time. So you have to check the question, whether question want you guys to find the initial rate of reactions, or we want to look at the particular times only, or we want to look at the overall rate of reaction. Are you clear? So if you check, the rate of reactions always highest at the beginning. Okay, so the question here is why highest at the beginning? So highest at the beginning because our substrate concentration is the highest. Correct or not? Because you will follow the entire course, you will realize that the volume O2 now produced per minute or per unit time decreasing until zero. So what we do know that initial part here, that time equal to zero, the substrate having the highest concentration. So that's why enzyme control reaction always highest at the beginning. But provided that, this is the term and conditions. What is the term and condition? You must have, make sure that enzyme concentration is not a limiting factor. Means that in this case, guys, I have more enzyme that can catalyze my reaction. Are you clear? So that I can get the initial rate of reaction. If your enzyme as a limiting factor, not enough enzyme. If not enough enzyme, then the initial rate of reaction is not true already. Are you clear? Okay, the true value cannot be shown. So in this case, term and conditions, the enzyme is not a limiting factor. It means that we have sufficient enzyme. Therefore, the rate of reaction always higher at highest at the beginning, but gradually you can see that the steepness of the tangent here, the steepness of the gradient will continue to decrease until 0. Horizontal line, 0. So means that the moment it becomes plateau like this, then we know that if I drag a line down, I know that at this time point, the rate of, the time point here basically means that at this time, all reactions have been completed or stopped. Okay. So it depends on the type of question. Later, I will show you guys a different kind of questions. Then you will be able to understand it better. Okay. So in this case, we measure the initial rate of reaction. Normally, we like to use the initial rate of reaction because the value always the highest. And we do know that at the initial part, the concentration of the substrate is the highest. Okay. Because at different moment, the concentration will not be the same. For example, here I made 100 unit of substrate. Because of conversion, I may become 90, 60, okay, until no more 0. So therefore, we always take the initial rate of reactions for this kind of reaction. Okay. Now, I will have a session with you guys later on how to plot the graph. This is required by the practical skills. Okay, so this one I will move it later. Okay, don't plot, don't do anything. In this case, we continue with the theory part first. Okay,